Welcome back to ECE 442-542. Homework number 5 is not due Friday. It's due Monday. Exam number 3 is 2 weeks away. That's pretty close, so I was just thinking before class I need to start making material 3 for exam number 3 available on the web. I'll try to do that in the next little bit. Oops, I didn't put the due date. Somebody can remind me when the due date for 542 is. Okay, if we don't know it, we need to check and verify when that is. But project for 542 students is due before the end of the semester. And I don't remember the date, but please realize that you do have a project to complete. Our goals for today, hopefully no April Fool's jokes. That's one of the goals. I will start actually with helps and hints for homework number 5. Who has started homework number 5 since it's due on Monday? That's what I was afraid of. But hopefully pardon? Is it due on Saturday? I thought it was due on Monday. Monday, April 6th is when homework 5 is due. But you should start on it, and I hope after these quick run-throughs or scrolls through it will maybe save you some time in that process of completing homework number 5. That's one of the goals for today. A second goal is to basically summarize the direct design method of Ragazzini, and that has the potential to have 4 restrictions. It has the potential. There may be restrictions. 4 on the overall closed-loop transfer function between the reference input R and the output Y. And I hope after today's class you are much more comfortable with that design process. We'll go through an example of that. And is everyone here and elsewhere comfortable with when I say a deadbeat response? Do you know what that means? And I explain it on the board, but I want you to realize what that means. That means your denominator is just z to the sum power. All of your denominator roots are at the origin. When I say deadbeat response, and let's say you have a 5th order system, in the denominator of your t sub c of z, you would have z to the 5th. You don't have to do any more thinking about where your poles are located. If I say deadbeat response, they're all at the origin. Is that clear now if it wasn't before? And we'll go through that. That will be one of our first examples. And I think all of the examples on homework number 5 say your desired transfer function needs to have a deadbeat response. That means you don't have to spend time trying to figure out where do I want my poles. The first 2 problems on homework 5 will be where do I locate my poles to meet these performance specifications. After we go through the first, thought maybe I'd unplugged my mic, but if I can hear myself, I haven't unplugged my mic. When do these restrictions apply? As I said, the 4 restrictions on designing t sub c of z may or may not be necessary or have to be incorporated into your design, and we'll talk about the cases when they do not have to be applied. After our first example, we will have another example. I don't know how far we will get, but then we get to see intersample ripple. And ripple is not a drink. Sorry. But ripple, do you have a visual for what ripple is? If you have ripples in the ocean, just little ups and downs. Intersample ripple means that in the output response, you actually might have your signal or your output going up and down in between your sample points. Rippling. That's what's meant by intersample ripple. And we might get there, we may not, but we'll see how far we get in today's class. Here are some hints for homework number 5, and I'm going to scroll through these quickly, but hopefully you will be able to go back over these after today's class and before you complete homework number 5. On problems 1 and 2, you basically can start with your desired transfer function, capital T sub c of z, having a very simple numerator. Just a gain and a 0 at the origin. And most of your process of completing the assignment is selecting alpha 1 and alpha sub 0 in your denominator polynomial. That's the main point behind problems 1 and 2 on homework number 5. Meaning we want to pick alpha sub 0 and alpha sub 1 based on performance specs, which we've covered in previous lectures. And I think this semester those were lectures on the 23rd and the 25th of March. Based on those lectures, which were, what performance specs do we think about in this class? Settling time, which is right there, percent overshoot, and peak time. Those are the 3 that we're focusing on. Those all imply certain relationships or values for the locations of your closed loop poles. In particular, if you're interested in analyzing the settling time spec, that immediately, when you hear settling time, you should start thinking bullseye or concentric circles. That influences your radius of the dominant poles of your desired denominator polynomial roots. And here we have, let's say, a settling time. You can get the 1% settling time from this relationship of the radius raised to some integer value, which we're labeling as capital N set, equal to 0.01. And if you solve that now for R, based on a settling time, you now know where the radius of your poles are. And again, I was challenged with my circles, but I have a challenged with my colors now. I have a green circle and a blue circle. The blue circle represents poles that are faster settling time, because the radius, the distance those triangles are away from the origin, R sub 2 is obviously smaller than R sub 1. To be stable, what do those 2 circles need to be? They both have to be inside the unit circle, don't they? If we are dealing with stable poles, you know then that R sub 1 needs to not only be maybe there, but inside this unit disk or unit circle in order for those poles to be stable. And if you want a faster response, you want a smaller circle. You want your radius to be collapsing with speed in the z-plane. That's problems number 1 and 2. Oh, the other thing is you have the possibility of having 3 different design specs or performance specs. What if you're only given 2? What do you do about the third one? Guess. Choose it based on your other specs. Any other answers? Do you have flashcards that you can show me how you would pick your flip a coin? Put your thumb up, put your thumb down. If you're not given a performance spec, you don't have to worry about it. You can neglect it, and it can just be whatever results from your other two performance specs. If you're just given a settling time spec, you don't have to worry about the angle or the heart, the logarithmic spiral. You just have to worry about the radius. You can make the others whatever you want. Is that clear? So if you're given two performance specifications, you don't have to try to solve for the third one or meet some other third performance specification. That can be left alone, and it can just be whatever it results in being. If you're given all three, they may not all be consistent, and you may have to collapse or constrain one or two to make all three satisfy. Is that clear? And I think we talked about that before. That's problems 1 and 2 on homework number 5. Problem 3. I'm assuming you are starting with a zero-order hold equivalent to obtain capital G of Z. I may give you an analog plant, G of S, which is 1 over S minus 1. Is that plant stable or unstable? G of S equal to 1 over S minus 1. Is that a stable open loop plant or an unstable open loop plant? Where's your pole? The system, this is low enough on the screen, I can't do this for those of you online, but I can cover up the S. I just have G of S. Ooh, that screen is sticky. Does anybody have some cleaner? Yeah. I don't know who spilled something on the screen, but it's awfully sticky. Sorry, the ones at home. Oh, somebody's offering me some cleaner, some hand cleaner. No, thank you, though. I've wiped it off now. I'll have to clean my britches when I get home. Where were we? Oh, I was trying to give you capital G of S, which is just 1 over S minus 1. Where's the pole? Right half plane. Is that stable? No, not for a continuous time system. So you are trying to now stabilize an unstable system. But the first thing that you need is to find a capital G of Z. You can find it from this. And if you have MATLAB available to you, which I don't mind you using, and now I've already given you the answer, capital G of Z is just this small number in the numerator over Z minus 1.1052. Is that system stable? No, better not be. It's just the discrete equivalent of what you started with for the analog system. The analog system was unstable. This one, its pole is outside the unit circle. It's unstable, consistent with G of S. Now what you want to do is design a controller based on this capital G of Z. And the controllers that we're dealing with are based on this Ragazzini approach, which means we need to start with some desired closed-loop transfer function. And the desired closed-loop transfer function needs to satisfy certain relationships, and the main one here is, what's the pole zero excess of capital G of Z? How many poles do you have? 1. How many finite zeros do you have? None. 0. Your pole zero excess? 1. So you need your T sub C of Z for the causality constraint to have a pole zero excess of 1. And if you want a deadbeat response, where do you put the pole in T sub C of Z? At the origin. Is T sub C of Z have a pole at the origin? Yes. You set the denominator equal to 0, and what value of z satisfies that? Z equal to 0, right? And how many more poles do you have than zeros in t sub c of z? 1. So it has at least the same delay as your original plant, capital G of z. So I would recommend or suggest that you try this for your t sub c of z. I'm working these problems for you, or I'm hinting, so that I want you to start getting through these and understanding what's going on without spending a lot of time spinning your wheels. Problem number 4. I think I give you this capital G of z. I give you a discrete time system, plant, capital G of z. What's the pole zero excess of that capital G of z? These questions are very challenging, right? We have a pole zero excess of 1 in capital G of z. We had 2 poles and 1 0. We end up with a pole zero excess of 1. That means that t sub c of z, our desired closed-loop transfer function, must have a pole zero excess of at least 1. Has to be consistent with G of z. Now, looking at G of z as a transfer function, it has an unstable pole, 0, neither. Capital G of z, where are your poles? Those aren't hard to find, are they? They're the values of z that cause the denominator to vanish. You have 1 at the origin. Is that very fast or is that slow as a pole? That's fast. That's a fast pole. Where's your other pole? At 0.9. It's in the right half plane. Is that a problem? No, that's a good thing, actually, as long as it's inside the unit circle, which it is. It has a magnitude less than 1. Your poles are both stable. They're both inside the unit circle. Where's your 0 located? Outside at 1.1. We have an unstable 0. These now, this may not make as much sense, but after today's lecture, I hope it will. But when you scroll back through this weekend or maybe tonight, now we will talk about restriction 2, which says if you have unstable zeros in G of z, you need to retain those zeros in T sub C of z, capital T sub C of z. That means if you have an unstable 0 factor in G of z, you need to put that same factor in capital T sub C of z. That's the second restriction, which we will talk about in a minute. And if we want this to have a deadbeat response, we put all of the poles at the origin, and T sub C of z has to have what kind of relationship between its poles and zeros relative to capital G of z? That's the causality constraint. That's restriction 1. We have to have the same pole 0 excess in capital T sub C of z as we have in capital G of z. And our pole 0 excess in G of z was 1. Does this proposed capital T sub C of z have the correct pole 0 excess? Yes. It has 1, 0, and 2 poles, a pole 0 excess of 1. What you don't yet know is that gain k. That's what you'll have to find by solving problem 4, is what's my gain k in this desired transfer function. That's what you're looking for. Questions on that homework help? You may not know what's coming since I didn't see very many hands go up when I asked who has looked at or started homework 5, but now I think you have more clues or hints to work from in solving homework number 5. Let's now talk about the direct design method of Ragazzini. I just like saying that, Ragazzini. That's a person's name. And this design approach was named after this person. And there's really just 2 steps to this design. But there's a lot baked into that first step. But the first step is to create or build or design, come up with a capital T sub C of Z. That's the first step. And there may be, and the key word here is may. There may be restrictions, constraints on T sub C of Z. There definitely is going to be one, which is the causality constraint, which says we need at least the same pole zero excess in capital T sub C of Z as we have in G of Z. Is that clear what I mean by that? You have the same amount of delay between your input and output in your plant as you have in your desired closed loop transfer function. You can't speed up your system in terms of delay. You have to have at least the same amount of delay in your desired transfer function, capital T sub C of Z, as the original system. That's just one of the constraints or restrictions. The second step, and we'll talk about 3 more. So there's 4 possible restrictions. And that's what we'll quickly go over, and then we'll work through those with an example or 2. The second step is once we have T sub C of Z designed or built, and we have our plant, capital G of Z, then all we have to do, it's not that, it's just turning the crank, plugging those 2 transfer functions in to this direct design formula to produce your controller. That's what capital C of Z is. Your controller that will produce in the closed loop capital T sub C of Z as your closed loop transfer function. And if you observe the correct restrictions or constraints, you will have an internally stable system that satisfies your properties that you're after. What are these restrictions or constraints? There's 4 of them, and I'm calling them R1, R2, R3, and R4. R1, restriction 1, or constraint 1 is the causality constraint, and we talked about that at length last time, or quickly wrote down some things, but that basically means that you want the degree of your controller's denominator to be at least as big as the degree of your numerator in your controller transfer function. And that constraint or condition on capital C of Z on your controller means that you have the same delay in your desired transfer function, T sub C of Z, as you have in your original plant, at least as much delay. Or the pole zero excess in T sub C of Z is at least as large as the pole zero excess in G of Z. That's restriction 1. Restrictions 2 and 3 are imposed or are created to preserve internal stability. And to preserve internal stability, we did not want our controller canceling unstable poles or unstable zeros. That's the idea behind restrictions 2 and 3. Those restrictions are then as follows. Restriction 2, and it really doesn't matter how these are numbered. This just gives us a way to talk about them. If I say restriction 2 or if I say restriction 4, you'll know what we're talking about, but really doesn't matter that one is 2 and one is 3 and the other one's 4. I'm just labeling them. Restriction 2, the way I've labeled it, is that if you have unstable zeros in G of Z, those need to be present in capital T sub C of Z. If you have a 0 at 2, Z equal to 2, then you will need a factor Z minus 2 in capital T sub C of Z. And that will prevent you from having that 0 canceled by your controller if you include it in T sub C of Z. And you can sort of see that if you look at the design formula. Restriction 3 concerns unstable poles in capital G of Z. If you have poles outside the unit circle in G of Z, you need to make those become zeros of 1 minus T sub C of Z. And we'll work through what this means or looks like via some examples. That's restrictions 2 and 3. It's all dealing with preserving internal stability. The last restriction is steady state accuracy. And here I'm just very quickly saying what this can mean. Steady state accuracy is what's happening after the transients have disappeared. What's going to happen in the steady state? And that usually means that you're applying the final value theorem or looking at what's happening at large time horizons. Steady state accuracy may impose additional constraints on this desired transfer function, T sub C of Z, in the limit as Z goes to 1, which means as we go in frequency to DC. And that's what's going to happen in the steady state. This will make more sense, I think, when we look at it as an example. But all 4 of these restrictions concern the structure or the creation of the desired transfer function T sub C of Z. Let's look right now at an example of restriction 4, just so that you maybe get a little bit better feel for what I mean by steady state accuracy. If we're dealing with steady state accuracy, we are probably interested in the error signal in our block diagram or in our closed loop transfer function. And what's the error signal? If we have unity output feedback, that's the difference between our reference input and the output of our controlled system. That's the error signal. But we know, or we have, an expression for capital Y of Z. In terms of R of Z, Y of Z is just the desired transfer function, capital T sub C of Z times R of Z. This is Y of Z by definition. Well, we have an R that's common to both of those pieces, or both of those terms in that error expression. I can then factor those out. And now my error expression is the quantity 1 minus T sub C of Z times R of Z. Now, what if we want 0 steady state error? Suppose if we want 0 error due to a constant input What's a constant input, let's say of magnitude 1, going to look like for our reference signal R of z? If I say R of z is a constant of magnitude 1, what does that look like in the z transform domain? What's R of z? R of z is a unit step, let's say. What is R of z as a function of z? You remember? Do you have your z transform table burned into your noggin? Do you remember what that is? Is that what it is? Z over z minus 1. If R of z is a constant, z over z minus 1, and we plug it into this formula, we want in the limit, which we can determine from the final value theorem, we can now say that the limit as time marches off to infinity, little e of infinity, is the limit of our error as n goes to infinity of little e of n. But our final value theorem in the discrete time setting says that we're interested in that being, or we can say that that's equivalent to the limit as z goes to 1 of the factor z minus 1 times e of z. But we have an expression for capital E of z. This is now the limit as z goes to 1 of z minus 1. We have 1 minus t sub c of z times r of z, but r of z is z over z minus 1, and this z minus 1 factor cancels that one. And what happens as we let z go to infinity? I'm sorry, as we let z go to 1? What happens to the far right z? The limit as z goes to 1 of z, 1. So that one goes away, doesn't it? What happens inside? Well, 1 stays 1, but we let z go to 1. This now becomes 1 minus t sub c with z replaced with 1. And if we want zero error due to a constant input, we would want little e sub infinity to equal 0. And now we have one equation that involves whatever is inside capital T sub c of 1, and that might be a gain. We can now solve this equation. What does T sub c of 1 represent? What's another way of describing that as an expression or as a concept? What is capital T sub c of 1? Pardon? That's our DC gain, isn't it? That's the DC gain of our desired transfer function. This is simply the DC gain of the CLTF, closed loop transfer function. And that makes sense. If we want zero error due to a constant input, we want to inject 10, let's say for R, that gets passed through eventually, hopefully a stable closed-loop system, but the gain at DC is 1, so we will get 10 out of that system. We'll have an error of 0. That's an example of restriction number 4, or a particular constraint on our desired closed-loop transfer function. This says that you could then take your t sub c of z, set z equal to 1, and solve for the unknowns that you have in t sub c of z, and you want those to give you a value of 1. That will then satisfy restriction 4. And that's based on steady state accuracy. Let's now work through an example. Let's say from start to finish. Suppose you're given a transfer function of a system that you're asked to control, and it has a gain of 4, or let me just say a parameter of 4, times the factor z minus 1.5 over z minus 1/2 z minus 2. What are some observations that we can make based on what we know needs to be true in creating or building this desired transfer function, capital T sub c of z? What are some observations that we can now make on G sub c? On G of z? Based on what we've already sort of foreshadowed, we need to be taking into account in our design of capital T sub c of z. Do you remember some of the restrictions? What's the causality constriction tell us? Causality restriction tell us? Or what's it concerned with? It's the degree of the numerator and denominator, or what we're calling the pole zero excess, aren't we? In this case, G of z has a pole zero excess of 1. We have 2 poles and 1 0. We need our T sub c of z to be at least having a pole zero excess of 1. It could have a pole zero excess of 2 or 3, but it can't have a pole zero excess of 0. What are some other observations that we need to keep in mind as we build this capital T sub c of z? It has an unstable 0, doesn't it? G of z, our original system. So G of z has an unstable 0. Where is that 0 located? At 1.5. And what do we know we have to make sure doesn't happen? We need to make sure that capital C of z does not have a pole trying to cancel that 0. So when we end up designing our capital C of z, we better look at the denominator of that and say, is there a factor that is z minus 1.5? And if it is, you go, whoops, I've done something wrong, because I can't be canceling that unstable 0. What else do we have in G of z? We have an unstable pole. Our system is nominally unstable. G of z has an unstable pole. And where's that? Are we all on the same page? Do we see that we have those three properties of our original plant, capital G of Z, that we have to keep track of while we're doing this design, while we're doing the construction of capital T sub C of Z? So now let's think about doing that. We want to look at the design of capital T sub C of Z, and just to keep us with notation that we can keep track of, let me say the numerator, I will allow that to be this polynomial n sub t for T sub C, and let's call the denominator polynomial little d sub t, where this capital T sub C is our desired closed loop transfer function. I'm assuming you're all going to go home and start texting this. That's why we're abbreviating all of these to CLTF. So when you start texting this to your mom or dad, Mom, I have to work on my CLTF, she'll know exactly what you're talking about. She'll say, I thought I told you not to speak that way to me. No. CLTF, closed loop transfer function. Now what do we do? Well, we need to make sure that something is true for the numerator polynomial based on restriction 2. R2 have T sub C of Z retain the unstable 0 from our original plant. What does that mean we need for little n sub t of z? What structure does that impose on little n sub t of z? It has to at least contain this factor z minus 1.5, doesn't it? Anything else is sort of up for us to play with. But we have to ensure that n sub t of z is maybe some other polynomial, I'll call that alpha of z, times z minus 1.5. It has to contain that one factor. It has to contain the same 0 that we started or had in our original plant, because our original plant had an unstable 0 factor. Where do we want our poles of T sub C of Z? Well, let's just for now assume we have a deadbeat response. So suppose we place the poles of T sub C of Z all of them at the origin. That means then that T sub C of Z will have a deadbeat response. Now, do we have any other restrictions that we know have to be satisfied? We've already accounted for this one, haven't we? Restriction, or this property of g of z. We have a pole zero excess of 1. That means our t sub c of z has to have a pole zero excess of 1, however we build that. And what else? We have an unstable pole, and restriction 3, if we went back to that somewhere, if we have an unstable pole or poles in g of z, then those have to be such that 1 minus t sub c of z has zeros where those poles are located. Which in this particular case then, restriction 3 implies that we need 1 minus t sub c of z evaluated at the unstable pole, which is z equal to 2. That needs to be 0. We have to have a 0 of 1 minus t sub c of z when z is equal to 2. And that's a way of sort of expressing that. Now, if we combine this with our pole zero excess and our desire to have a deadbeat response, and that polynomial in n sub t of z, what could we possibly try as an expression for capital T sub c of z? What's the smallest order of the numerator? What's the smallest possible order for the numerator? Second, how many zero factors do we know have to be included? Just that one, z minus 1.5, right? We know we have to have that factor. And I maybe threw you off by saying we have a polynomial alpha of z. But that polynomial could be a constant, couldn't it? As to make it as trivial as possible. It could just be a gain k. Let's try that. Let's try the simple before we go any more complicated. The numerator then could be maybe k times z minus 1.5. That satisfies restriction 2. A deadbeat response and our causality constraint, which says we need the pole zero excess of this guy to be at least 1, what would that impose on the denominator? What's the denominator look like? Z squared. Is it clear where that came from to try that? We don't know what k is yet, but we do know we have to have a factor z minus 1.5 in the numerator. We know we have to have one more pole than 0 because of our pole zero excess, and we agreed, because we said we were going to live with a deadbeat response, that we wanted all of the denominator roots to be at the origin. That's where that z squared came from. We needed 2 roots in the denominator, and they both could be at the origin. So you could say z minus 0 times z minus 0, z squared. All right. So in this case, we've satisfied, so for this transfer function right now, t sub c of z has the correct pole zero excess. Now, we need to see if we can pick that gain k to allow us to meet restriction 3. We haven't yet verified that we have satisfied restriction 3. And will k be enough parameter flexibility to allow that expression to be true? Meaning, with the location of the unstable pole, at z equal to 2, that implies 1 minus t sub c of 2. That's a 2 and not a z. That's now 1 minus, we had k, z minus 1/2, but we're replacing z with 2. And we had z squared in the bottom. And we actually want that, when evaluated at z equal to 2, we need that to be 0. That's one equation, and there's only one unknown. We can solve for that k from that restriction. This now tells us that k times 2 minus 1/2 gives us 1/2. All of that needs to equal 1. That's just coming to us from that expression. Just solving that expression. Now I have k times 1/2 over 4 equaling 1. We solve that for k. I actually have k over 2 cubed equal 1. And 2 cubed is 8. We now know what t sub c is. It's now 8 z minus 1.5 over z squared. That's our desired closed loop transfer function. We're basically pretty well done, except we need to now find our controller, capital C of z. But we have a design formula to do that. Let's now find the controller. Which says that capital C of z is now 1 over g of z times t sub c of z over 1 minus t sub c of z. This is our design equation. Now all we have to do is plug in the transfer functions that we have already, that we possess. We now have c of z is 1 over, and what was our plant? Our plant was 4 times z minus 1.5 over z minus 1/2 z minus 2. Is everybody okay with that? We're just plugging in capital G of z, and G of z was our original plant. We had an unstable 0 and an unstable pole, and we had another pole at 1/2, and we had that constant 4 out in front. Now we plug in T of z in a couple of different places. And T of z was 8 z minus 1.5 over z squared, all over 1 minus 8 z minus 1.5 over z squared. This factor, z minus 1.5, can cancel. I can cancel some of that 8 with the 4. And now I simply need to sort of simplify this expression. But do you see that I now have z squared and a numerator? If I get a common denominator in both terms, 1 is just z squared over z squared, so I have z squared minus 8z plus 8 times 1 and a half. And half of 8 is 4, so I have 8 plus 4, or 12. That's just what's in the denominator of that mess. But these z squareds are the same, they cancel. And now I have capital C of z, and I have a denominator in the denominator. That flips upstairs. I have z minus 1/2, z minus 2 all over. I've canceled everything in the numerator in the denominator, so that's just 1. And what do I have in the right-hand big bracket? I had a 2. And downstairs I had a z squared minus 8z plus 12. After I've already canceled the z squareds in the denominator of the numerator and the denominator of the denominator. Is it clear where that blue expression came from? It's just algebra. Now we need that factor z minus 2 to go away, because we don't want to be having that pole zero, that unstable pole cancellation with our controller. And that was an unstable pole in our plant. So if we factor this z squared minus 8z plus 12, that factors nicely. And now that goes away from our controller, right? We didn't want it in our controller because we knew our controller cannot cancel an unstable pole in our original plant. What are we left with then for our controller, capital C of z? We just take everything that's left. We have a 2. We have a z minus 1/2. And we have a z minus 6. That's now our controller. That was pretty slick, wasn't it? If you've taken another control class, sometimes finding this controller is hard. Now the challenge in this design approach is creating the original desired closed-loop transfer function, capital T sub C of z, based on the restrictions or constraints. This is now our controller, and we have our plant. We can now find, using that controller and plant combination, here's R of z. We have our controller here, and we know what that looks like. That's right there in the black box. We have G of z, our plant. That's what we started with. There's Y of z, and we've agreed that we're in a unity output feedback configuration. And if you do the algebra on C and G, you will find that that overall transfer function between R and Y is indeed 8 z minus 1/2 over z squared. T sub c of z is just GC over 1 plus GC. And if you did that algebra, it would all boil down to what we said it should be, capital T sub c of z. Are you curious what this looks like in terms of a system behavior? If we kicked this system with R, what's Y going to do? And now you can actually solve this with a napkin. You don't have to have MATLAB to do this analysis. That's one of the beauties of doing some of these digital control problems. Let's look at the time response. Behavior of T sub c of z. And we've claimed it's a deadbeat response. Let's see if that's actually true. T sub c of z is the relationship between the reference input R and the output Y. So that's the transfer function Y over R. And that's 8 z minus 1.5 over z squared. And we want to basically analyze this. Well, we can clean this up by multiplying by 1. A nice way of writing 1. We want to turn this into a difference equation, relating R's and Y's as functions of time, or little n. And if we put this in terms of delays, now we have capital T sub c of z as 8 z to the minus 1 minus 12 z to the minus 2 all over what's in the denominator. Z squared times z to the minus 2. We can add our exponents and we have z to the 0, which is 1. Ooh, this is nice. Now what do we know? Now we know if we cross multiply, we have y of z times 1 is equal to 8 z to the minus 1 minus 12 z to the minus 2 r of z. And we are electrical and computer engineers, so we can easily think in the frequency domain or the time domain, can't we? This is now in the frequency domain, but can you now see what that looks like in the time domain? That's trivial, isn't it? Knowing what you now know. What's on the left in the time domain? That's just y of little n. What's on the right-hand side? We have, I'll do the hard part, we have a gain 8. Z to the minus 1 r of z. What's that in the time domain? That's just little r of n minus 1 minus 12 r of n minus 2. That's now our closed loop linear finite difference equation. And you can analyze this without having to do differential equations. This is just a recursive formula. This just tells you how r's and y's are related, and there's not even any memory in this guy. There's no y of n minus 1 or n minus 2. It's all just based on r's. Why don't we just look at a simple case? Let's let r of n be a unit step. or little r of n is equal to 1 for all little n greater than or equal to 0. If that's the case, based on this expression for little y of n, what's y of 0? Well, that's just 8 r of 0 minus 1, or r of minus 1 minus 12 r of minus 2. And based on that formula for r of little n, r of minus 1, 0. R of minus 2, 0. So the output at time 0 is 0. What about y of 1? That's now r, 8 r of 0 minus 12 r of minus 1. What's that? That's just 8 times 1, because r of minus 1 hasn't kicked in yet. What about y of 2? Don't you wish your differential equations were this easy? You're simply analyzing this system's behavior. What's y of 2? Well, that's 8 r of 1 minus 12 r of 0. Is that minus 4? What's y of 3? Is that any different than y of 2? What's y of 4? Y of 5? Y of 6? Have we beat this guy to death? Is this a deadbeat response? Is it going anywhere after a certain length of time? It's stuck at minus 4. Yes? If we hadn't neglected what? Yes. So now the question was, you neglected one of our restrictions. Restriction 4. We didn't impose that, did we? What's this? Before I get to answering your question, don't let me forget that question. I'm visual. I want to see what this looks like with respect to time. I now am plotting y of n relative to n, and the first y of 0 was 0, but then it jumped up to what? It went all the way up to 8. Then what happened? Then it jumped all the way down to minus 4, and then it stayed there. That's what the transient looks like, or the response y of n. The question was, or what's the steady state error now in this system? What did we put into this system? What was the reference input? That was just 1, wasn't it? We had a unit step. What's the output? What's y of n for large n? Minus 4. What's our error? What's our steady state error? If we define our error to be r minus y, we have 1 minus a minus 4. What's our steady state error? 5. That may be too big. The question was, could we have reduced that or made that smaller by maybe imposing a steady state error specification, which we didn't touch, did we? We didn't say anything about our steady state error. And that allowed us to have a pretty straightforward capital T sub c of z. We tried the simplest, just a first order numerator and a second order denominator with one unknown parameter k. Now maybe we're not happy with this behavior. But do you see that it's deadbeat? How many times it just takes a couple of time intervals, sample periods, before it settles and never moves beyond that final value. That's the deadbeat response. It immediately locks in after 2 sample periods at a final value and never budges from that if we're not wiggling R. If we change R up here later, then this will do some more transients and then settle after 2 samples. But if we're not happy with this large steady state error, we may want to impose a steady state error or a certain steady state accuracy. And that will then maybe impose more structure on capital T sub C of Z. Meaning we might have to put, our numerator might have to be more than first order. We might have to put a Z minus alpha factor in there in addition to Z minus 1.5. And we have a K. Now we have 2 variables that we can adjust. Maybe if we say, let's have a steady state error of 0. Meaning if we imposed a R4, maybe we are concerned with constant inputs and we want 0 error to a constant. What does that impose on T sub C of Z? We want 0 error. What does that impose on T sub C of Z? Or where are we interested in the behavior of T sub C of Z? We want to know what it's doing at DC and what would we like it to be if we want 0 steady state error. We want that to be 1, don't we? So that if we injected an R of 2, the Y would be 2 after the transients. Well, what happened to our T sub C of Z? Which was, what was it? Was it 8? I can't even remember. Z minus 1.5 over Z squared. Is that what it was? Why does that not seem right? Because it's right. What's the DC gain here? Is that right? T sub C of Z is minus 4. That's not going to give us a 1 for T sub C of Z, is it? So now we might have to go back and say, well, I need to put more, I need to make T sub C of Z a little more complex. Maybe try T sub C of Z equaling K Z minus alpha Z minus 1.5. What's the denominator need to be now? If I want it to be deadbeat, if I want a deadbeat response, what's the denominator? Pardon? Z cubed, isn't it? We want all of our roots at the origin and we need the denominator to be at least one bigger in order than the numerator. So now we would need this to be z cubed. How many parameters do we have to play with now? What are our design parameters? We haven't yet specifically specified t sub c of z, have we? We have k and we have alpha. What do we have to be assured of here? We have to make sure that the zeros of 1 minus t sub c of z, when evaluated at z equal to 2, we have a 0 there, and we need a t sub c of z with z equal to 1 to be 1. Maybe we can satisfy those two constraints or those conditions with these two parameters. Does that answer your question? Now, what if, shoot, we're out of time, aren't we? But I think we can stay another hour. I may have to put together another hour or so of material that you can watch to work through another example. But what if we do not have a design constraint? We didn't have R4, did we? We didn't have a steady state accuracy, so we avoided worrying about it. What if you didn't have any unstable zeros in G of Z? You wouldn't have to worry about R2, would you? T sub C of Z, you wouldn't have to force it to have a zero factor of a specific type. What if you didn't have any unstable poles? Then R3, you wouldn't have to worry about restriction 3. Is that clear? You're always going to need to worry about your causality constraint, but the other three may not be on the table, depending on what's asked. Is that clear? Look for an email or more information on D2L, but I'll let you go, I guess, tonight.